So welcome to the session on Verilog Quick Start. So this is the first session on dealing with Verilog, and basically in this session we aim to touch upon the lexical conventions of the language. So lexical conventions are mostly like the grammar part of any language. It's not apps. It looks that it is not necessary that we should understand the grammar for the actual usage, but the importance comes of understanding these when you are trying to debug, okay, or when you are trying to optimize our code. Only if and only if we know what are the syntax part of the correct syntax of using each construct, what are the different grammatic rules that are applicable, what are the default values of certain usages, only then we will be able to sail through the debug process very quickly. And the same applies to writing flowless code. Now in this particular session we attempt to understand the reason why we are going to use any hardware description language as a design entry mechanism, and how a hardware description language is used in the VLSI design paradigm. What are the advantages of using a hardware description language? Why we are picking Verilog as our choice? And what are the different resources which we can rely upon in learning Verilog? What are the different lexical elements in Verilog, like ports, its classifications, data types supported by Verilog, the operators available in Verilog, and the nitty-gritty part of the differences of usages, how numbers are represented in Verilog. We also see certain data structures like vectors and arrays, how they are declared, how they are initialized, how they are selected for part usages. We also will be seeing certain special constructs like compiler directives as well as system task, which are available in Verilog. So if you look at the background of why we should learn it, this chart can give you a clue. This is called the Y chart in the VLSI design. So this gives you important considerations in making a design ready for a silicon. So the axis shows the different domains of designing. One is the behavioral part of it, or the algorithmic aspect, and the other one is the structural domain, which talks about the gate level decomposition or how the actual structure of the circuit would be. And the third domain represents the physical domain, which basically talks about the transistor layout, module layouts, floor plans, physical partitioning, and so on. So if you look at it, we require an entry mechanism, or the design entry mechanism should be able to penetrate through different concentric circles in this. Different concentric circles here represent different element in each domain. For example, we may require the design sometimes to be entered in an algorithmic way. Okay. Sometimes we may know the exact gate level logic. Sometimes we know how data transfers between functions and so on. So we require a design entry mechanism that can support multiple of these concentric circles. The reason why we are basically aiming at hardware description language compared to the counterpart of schematic, which is more of structural in nature. Now, if you look at the motivation, this is one important aspect that Verilog or any hardware description language for that matter support, which is not really supported by other design entry mechanisms like schematics. So we can call it as look ahead synthesis, because if you are doing it in the design is entered using a hardware description language, one obvious advantage is that it can be used to thoroughly debug the design before we go to the more time consuming processes involved in the synthesis. I already explained, synthesis here means converting our seamless if you are using a hardware description language compared to schematic entry. So we can write the description as a Verilog code. We can give it for functional simulation, where the code which we have written or the description of a hardware which we have written will be subjected to different test cases that will expose the correct functioning of the design as per the specification. Also, we can use the same Verilog or an extended version of it called System Verilog for writing verification exhaustively as possible, so that every single corner case or every single case that a hardware can fail can be explored before we go for synthesis. So the synthesis will become very smooth if you are using hardware description language. Also, if you are looking at hardware description language, it carries a lot of advantages. For example, it is highly scalable. So scalable in the sense that we write a Verilog code for a particular width or a bit size. Say we have written a code for a computing unit which works on 8-bit. It's relatively easier to scale it up to support 16-bit. This is not that easy in the case of a schematic entry. Another thing is its reusability. It can be used over and over again. Also, it support design abstractions. By design abstractions, what is meant here is it support different styles. There are multiple styles supported by Verilog, like algorithmic style is there, data flow style is there, gate level style is there, also transistor level style is there. We will come to that each one in detail. Also, compared to schematic, Verilog is easy to debug because with the help of compilers, we will be able to point to the exact lines of code where the bug possibly exists. We can go on debugging it in a stepwise process, which is not that easy in the case of a schematic design entry. Also, Verilog support hardware design co-design. You can put the hardware in loop and work with the code, and if the hardware outputs are not matching, you can always work upon the code, correct it, and then again put it on the hardware and make the hardware work. So a vis-a-vis comparison called hardware software co-design is quite well possible in the case of Verilog or HDL, which is not that easy in the case of a schematic entry. Also, because Verilog being reusable, scalable, modular, the design cycle it takes is much less, and this will result in less time to market for the product is concerned. Also, Verilog is highly vendor neutral because it is governed by an international standard set by IEEE. Further, it is platform independent. By that, what is meant is you write a hardware description in a synthesizable way in Verilog. You can target that design to reside upon a field programmable gate array or a CPLD, or even you can target it for multiple technology node ASICs. So that independence is of high use when you are talking about a design which is going to be portable. Now, if you look at the important resources as far as Verilog is concerned, Verilog is actually a language. I will just touch upon the evolution of Verilog. Verilog was born in the year 1983. Later, it was acquired by a company called Gateway Design Automation and by Cadence subsequently. In 1995, Verilog got standardized by IEEE. Then came many revisions and versions and refinements to it. In 2001 came a revision, in 2005 came another revision, and so on. Now, if you look at the IEEE standard called 1364, stands for Verilog Hardware Description Language. So the IEEE standard citation is given. There is a 2001 version and possibly 2005 version also you may get to download. So this is called LRM or Language Reference Manual, which could be possibly the most authentic document about Verilog. Whenever you find some conflict in terms of Verilog descriptions in different textbooks, you can always rely upon this document. Also, for your information, there is another superset of Verilog which is called System Verilog. It is also another IEEE standard called IEEE 1800. This is nothing but Verilog plus certain object-oriented programming concepts and support for certain methodology which makes the verification of complex VLSI design easier. So if you want to learn system Verilog, the obvious step is learn Verilog thoroughly and pick up the object-oriented programming concepts and verification constructs which are unique to system Verilog. And by now Indian standard, at least I would say that if you know system Verilog and Verilog pretty well, getting an employment and all, it would be quite easy, because there is a dearth of professional design verification members in almost all semiconductor design companies. Now, certain resources which you can very well easily access are these books. There are at least some 100 high quality textbooks available in Verilog, but these are my picks. The first book is a textbook on Verilog HDL, a guide to digital design and synthesis by Mr. Samir Palnitkar. The second book could be a book which explains about certain nitty-gritty of the language while it is being used for synthesis. The Verilog HDL synthesis, a practical primer by J. Bhaskar. And also this book by Stuart Sutherland and Don Mills could be of use if you are trying to become a professional Verilog designer, because this book talks about different unexpected errors and how to avoid them. Okay. Now, if you look at how HDLs are used, as we already touched upon, hardware description languages are not programming languages. The key difference is that Verilog HDL is a concurrent programming language. By concurrent, I mean every single step or every single line what you write in Verilog basically get executed concurrently or parallelly, except certain lines which we deliberately write inside a procedural or a sequential box. So this is very much in line with the working of a hardware, the concurrent nature, which is not really part of the normal programming language. So when we are writing Verilog program, we have to write it with a mentality that why we are writing is basically ultimately to convert it to a hardware. So that is called RTL designing. There is a difference between RTL designing and behavioral designing. RTL designing here stands for register transfer level. By that, what is meant is writing Verilog description of a hardware in such a way that it can be converted to a structural equivalent by the process called synthesis. So we write a Verilog description in the RTL way or in the synthesizable way and put it for synthesis. The synthesis tool reads and infers your Verilog code. It finds out what should be the equivalent hardware structure or the gate level netlist, we call it. So gate level netlist seems like another textual file, but it is more about how the gate level composition of your design should be like this. You can see an example gate level netlist here. Now, once it is formed, it is subjected to a lot of backend processes as part of synthesis, like design partitioning, floor planning, routing, and so on, subject to the constraints set by the user. Then finally it is ported onto a hardware. The hardware platform could be a reconfigurable platform like a PLD, programmable logic device, or a PAL, programmable array logic or programmable logic array, or it could be somewhat more complex field programmable gate array also. Also, if you look at it, there is an option to use it for creating custom integrated circuits or application specific integrated circuits. Okay, this is how HDLs are used. Now, before we start with the rest of the Verilog, let us just take into consideration this design requirement which you may attempt to do. So this is the design of a magnitude comparator, which is a small piece of hardware. The specification is given in such a way that the magnitude comparator which we want to design should have two inputs, say A and B, both 3-bit wide, and it should have some 3 outputs, each single bit ones, which is basically giving the relationship between the input. If when you enter A and B at any point of time, one of these outputs should be high and the rest should be 0, because you give two inputs, either they are equal or A is less than B or A is greater than B. So depending upon what actual comparison this hardware makes, the output should come up. So this is a requirement. Now if you are not using hardware description language and trying to go for the schematic way of design entry, what we should do is we will have to draw a truth table and list out all the combinations. You see there is 3-bit A and 3-bit B, so there will be total 6-bit input to be compared among itself. So there will be 2 to the power of 6 combinations. It will be quite a big quantity of calculations to be done to arrive at the combinational circuit corresponding to this. Okay, it will take some time and always prone to error. Now towards the end of this particular session, we will see how quickly this can be accomplished in the case of a hardware description language, which may help you appreciate the reason why we are learning hardware description language. So I will keep it at bay for some time till we conclude this session, and we will revisit this problem once again. Now if you look at Verilog, in Verilog the most fundamental entity or building block is called a module. So a module can be imagined as a black box with lot of input pins, output pins, and also there could be some bidirectional pins as well. Okay, so what is a Verilog module? A Verilog module is nothing but a design block, or it could be a collection of one or more low level design blocks. So the Verilog module or description actually works like a black box. It hides the internal implementation to the rest of the design or the outside world. So how a Verilog description or a module or a piece of hardware described in Verilog interact with the rest of the world? It happens through something called ports, which are nothing but these input, output, in-out connections. So if you look at what should be inside the module description, a module will always have a module, the keyword module will be there. There will be a module name, which is a user given name. You can give it any name, but a module name should not start with a number or a special character. It can be in small letter or it can be in capital letters as well. And followed by the module name, there comes a list of all terminal ports. So by terminal port, what I mean, the ports which are either coming from outside, coming into the hardware, or ports which are going outside from the hardware, or ports which has both input as well as output nature. So that is about port declaration. Then inside the module, we will be declaring the ports as input, output, in, out, etc. Then if the module contain only one piece of hardware logic, it's fine. Otherwise, if it's a combination of multiple hardware, you will have to instantiate other modules. It is illegal to nest a module, so you can't write a module within another module. You can only instantiate it. I will explain the process of instantiation. Then you will write the functionality. The functionality of the module can be written in the module body using a lot of continuous or sequential statements. We will see each one of them. Then there could be some special way of usages called task and functions. And finally, once you have finished describing the entire functionality of your hardware in the module description should end with another keyword called end module. There is no space between end and module. Now if you look at what are the data values supported by Verilog, the Verilog, because it's a hardware description language, it supports 4 logic values. 0, which represent a off condition or a false condition, a logic 1, which can represent a true condition or a on condition, set, which can represent a tri-stated or a floating condition or a high impedance condition or a disconnection perhaps, or X, which represent an unknown condition. So if you look at a hardware, a hardware can be subjected to any of these conditions. It can be in a on condition, off condition, unknown condition, or in a disconnected condition, or a high impedance condition. To represent all these possible characteristics of a hardware, the Verilog HDL supports these 4 logical values. So here there is a complexity involved. So when I'll just come to that. Now let's see how numbers are represented in Verilog. In Verilog, the numbers are represented in the format size of the number, a tick mark or an accent character, the base or radix of the number, and comes the actual number. Okay. So here the size actually should specify the size of the number in bits. Then the base can be binary, octal, decimal, or hexadecimal. If you want to represent binary, use the letter B either in small letter or capital letter, O for octal, D for decimal, H for hexadecimal. Okay. And for the value, you can use the values 0 to F as well as X or set. If you are not certain about certain bits in a number, you can put an X there. For example, you see here it's written 8-HAX. It means it's an 8-bit number. It's a hexadecimal representation, and the first 4 digit is represented by A, which is 1010, and the last 4 digit would be X, because it's altogether an 8-bit number, and one character in XR represent 4 digits. So the initial 4 bits would be, one digit in hexadecimal represent 4 bit. So the initial 4 bit is earmarked for A, which is 1010 in binary, and the remaining 4 bits are represented by X. Similarly, this is 12-03ZX7. So it's a 12-bit number. The first 3 digit, the first 4 digit is represented by 3. Then comes set X as well as 7, which is because it's octal, it is represented like this. In the case of hexa, it's a 4-bit for each digit. In the case of octal, it is 3-bit representation per digit. So you can always specify the size. Ideally, this way of specifying a number is preferred, but on certain occasion you can always give unsized numbers. For example, you see in the first row it is given simply as 10. So there is no size specified, there is no base specified. If no size is specified, the compiler will automatically assign it a certain specific size. Typically it is 32-bit in most of the compilers. So a 32-bit number will be inferred. And what is the base? It looks for, but no base is specified, so the default base is decimal. This is a very important point. If no base is specified, the default base of the number will be decimal, and the value here is mentioned as 10, so it will be mentioned as the binary 10. Okay, so the internal storage, or the storage, whatever way you specify the number, inside the simulator it will be stored in binary format. Okay. Similarly, you take another example. This is 8-HC5. So it's an 8-bit number, and the format is hexadecimal, and the first number is the initial 4-bit represent C, and the remaining 4-bit represent 5. Okay. So here there are a few more things. If the Verilog expands the value of the number by filling specified size by working from right to left. Also, if you look at the size specified is smaller than the actual value, the leftmost bits will be truncated. You can see this example. So the number to be represented here is F0 or F0. So this number actually should consume 8-bit for full storage, but you have specified a size of only 6-bit. So a 6-bit hexadecimal representation will be carrying, the binary representation will be carrying first, the initial 4-bit, there must be 4 bits will be for zeros, and comes that for H. So it will get slightly truncated. In the case, the next example, you can see it's only F need to be represented. So it's all 1 1 1 1, and you actually allocated 6-bit instead of 4-bit, so the remaining will be 0 filled. starting from right to left. Okay, so that is explained in the first line. Verilog expands the value by filling the specified size by working from right to left. So initially this f is written and then it allocates 2 zeros, or rather it is 0 field to fill this size. Okay. Now there are certain other ways the numbers, the real numbers are represented. So for example 3e4 you look at, it actually means 3 times e should be read as 10 to the power of 4, that is 30,000. Similarly 5.8 e to the power of minus 3 here represent 5.8 times 10 to the power of minus 3, this particular number. So it must have values on both sides of the decimal point when you are specifying like this. So here e need not be case sensitive, otherwise you please remember the whole of Verilog is case sensitive. By that what I mean is all keywords which we use in Verilog should be in small letters. Now let us see how strings are used in Verilog. String is a a sequence of characters which are enclosed in a quotation. So string variable declarations are done in such a way that it uses 1 byte per string character. For example, suppose you want to store this number hello world. You count how many characters are there in this string. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 letters, then one more character as an exclamatory mark and one more character as the space in between these two words. So there are total 12 characters and each character will take 1 byte of memory for storing a string. Okay, so the variable which we are creating for storage of a string must have a width of total number of characters into 8. Here there are 12 characters to be stored as part of this string. So 12 into 8 should be the width of the variable called string var, which is used for storage of this particular string hello world. Now the next part of the module is basically ports. As I told, ports are those connections that a hardware uses to interface with the external world. So if you look at the ports in Verilog can be classified into 3 categories based upon certain criteria. Based on terminations, ports can be classified is input port, output port, as well as in-out port. So it's a keyword, in-out is a keyword, the whole of the in-out should be written in small letter only. The keyword in-out is used for those ports which are bidirectional in nature. Okay, that the port enters into hardware as well as exit a hardware. Such ports are declared by the keyword in-out. Now, based upon the data type it supports, ports can be classified fundamentally into 2 types. One is called the net data type and the other one is called the register data type. There are different keywords which are used for representing the net data type like wire, var, vant, triand, trior, etc. Most common we will be using a keyword wire. Similarly, for register data type, the keyword which is most prominently used is reg. Reg is the keyword and the other keywords are integer, time, real and so on. You also should remember what is the default value in each of this data type. The default value of net is high impedance or set, and the default value of register data type is X. So what I mean by default value is you created a port of the type net, and before you start feeding it with any value, there exists a value in that connection, and that value is called the default value. And in the case of net data type it is set, in the case of register data type it is X. Okay, for real it is 0 and so on. So based upon width, the ports can be classified as scalar port as well as vector port. Scalar ports are those ports which can accommodate only 1 bit of information, either a 0 or an X or a 1 or a Z. Okay, for example, you see the declarations here: input A or output B or in-out C or wire D or rich A. All these are representing ports having different category, but what is common in all these ports? They are all scalar port. They can accommodate only one bit of information. Now you look at the right side box. The other type of ports based upon the width of data it can accommodate is called vector port. Vector port can accommodate multiple bit of information. For example, you see the declaration input 7 down 0. It is pronounced as 7 down 0. Here it means the port A is of type input and it can accommodate 8 bit of information, that is bit position 7, 6, 5, 4, 3, 2, 1 and 0. Similarly, the port B is an output port which can accommodate 4 bit of information. Bus A is another port of type register and it can accommodate 2 bit of information. Bus B is another port which can accommodate 4 bit of information. Okay, so when you are specifying a vector, you can specify it in little endian manner or big endian manner. If you specify the width like this and the width is ending with a small number, you call it as little endian. If the number is ending with a large number like this, it's called a big endian representation. So it makes considerable difference when you are selecting things from a vector. I will explain it as we discuss about vectors and arrays in detail in the same session. Now let's understand what is the difference between these two data types. Net data type basically represent physical interconnect between two different elements in a module or between modules. So these are certain connections which need to be continuously driven with values, which don't have to store any value. So such ports are declared as net data type. So mostly in combinational circuits you find net data type often declared using the keyword wire, because those ports are always being driven by some logic gates or so, and nothing need to be stored there. Okay. On the other hand, you will find a second type of port which is register data type, often represented by the keyword RAG. They are used to represent variables which are supposed to store the data temporarily. It does not represent any physical memory or hardware storage, but certain variables which are supposed to hold the value temporarily. So mostly in sequential circuit, when you are designing, when you say for example you are designing a D flip-flop, it has to hold the value till the next active edge of the clock is received. So such elements are declared using the keyword REG. Now within the register data type, as I told, there are multiple subtypes. Example, the keyword REG, it is used for indicating those variables which are supposed to hold unsigned numbers. Okay, suppose you want to store signed numbers, say -32 and so on. You can use another keyword which is also register data type, a subtype of that called integer. Okay, so the arithmetic operations over integer produces 2's complement result. Similarly, there is yet another data type called real data type. The purpose of real data type is to store floating point numbers with double precision. For example, 3.14, 7.15. So you want to store such decimal numbers, you declare that variable of type REAL. The default value of real is 0. Similarly, there is yet another subtype of register which is called time. And time is very unique in Verilog. It is used for unsigned integer variable which can be up to 64 bit wide, specifically for storing the time values during the simulation. Now let us look at a quick look at what are the different operators in Verilog. In Verilog, actually there are 9 classes of operators, like arithmetic operators, then relational operators, equality operator, logical operators, bitwise or unary operators, or otherwise known as reduction operators, shift operators, conditional operators, concatenation operators, replication operators. So few of the operators are exactly the way it is there in other languages also. So what all operators are behaving differently, we will have a look at it with certain examples. Now arithmetic operators, as I told, addition, subtraction, multiplication, division, and here comes the modular division. I hope you know the difference between normal division and modular division. Normal division operator will give you the quotient of a division, whereas modular division will give you the remainder. Okay, if you divide a number with a 0 using normal division, it will produce an X or an unknown condition in Verilog. Now logical operators include logical NOT or logical negation. Then 2 ampersand, if you put, it represents logical AND. So logical AND means if you write A double ANDed with B, it means when A as well as B both are 1, the result will be 1. If at least one of these happen to be 0, the result will be 0. Similarly, there is a logical OR. Suppose you write A logically ORed with B. If either A or B happen to be 1, the result will be 1. If both happens to be 0, the result will be 0. So that's about representing a logic. Here the input can be a single bit, or in the case of arithmetic operator, the input can be single bit or multiple bit, and the result will be having the same size. Whereas in the case of logical operator, the inputs can be single bit or multiple bit, but the result is always a single bit. Similarly, there are relational operators like greater than or equal to, less than or equal to, and so on. Similarly, equality operators are there. This double equal to represent if two numbers are equal or not. This exclamatory mark plus equal to checks whether two numbers are unequal or not. Okay, so the problem with these two operators is that if one of the bit of the operand happens to be X or Z, the result will be unknown. So if you want to check only certain specific bit of two operators and you are careless about the rest of the bits, you can always use something called case equality, which ignores X or Z. Okay, it will check only well-defined bits, are they equal or not, and produce an output. We'll see examples of that. Now the other type of operators are bitwise operators, which operates on all bits of a vector. For example, the first one, or tilde symbol, is used for bitwise negation. So if you write tilde of 1 0 1 0, it will just invert every bit. Tilde of 1 0 1 0 will become 0 1 0 1. Okay, tilde of 1 0 1 0 will become 0 1 0 1. Similarly, bitwise AND is there, bitwise OR, bitwise XOR. This is an important addition. It's a bitwise OR, then bitwise NAND, bitwise NOR, bitwise XNOR, and so on. So here this can be used with two operands, or it can be used as a single bit as well. For example, if you write the same bitwise OR operator before a single operand, for example, you see here the variable A is declared as a 4-bit variable of type binary 1001, and if you write C is assigned with OR of A, okay, it basically reduces this vector A into one number. What it does is it ORs this first bit with the next bit. 1 odd with 0 is 0, that 0 odd with 0, 1 odd with 0 is 1, and that 1 odd with 0 is 1, and that 1 odd with 1 is 1, and the final result will be 1. Okay, so originally A is a vector. If you have performed a reduction operator on it, it reduces the vector into a single bit result. This A has been operated upon by bitwise OR to get a single one. Let's see a few more examples of bitwise operator. Bitwise operators, as I told, it operates on every single bit, bitwise. For example, let us take these two variables. A is 1000 and B is 0111. So if you perform bitwise AND operator, A ANDed with B, single ampersand means bitwise. What it does is, it position wise it will AND it. So 0 ANDed with 1 is 0, 0 ANDed with 1 is 0, 0 ANDed with 1 is 0, and 1 ANDed with 0. So the resultant A ampersand B is all zeros. Okay. So on the other hand, if I do bitwise OR, it does the same operation and you get all ones. Okay. Similarly, A minus B is used for subtraction. Now this comparison, the relational operator A greater than B or A less than B, it basically compares two numbers. Okay, for example, here you are comparing 1 0 0 0 is greater than 0 1 1 1, and this condition is true, so it will return you 1, representing true. Okay, similarly you are trying to compare A is equal to B. Since A and B are unequal, the result will be false, represented by a 0. Okay, similarly sometimes you will find operators used like this as a chain. For example, here what we have done is not of A greater than B. So this simple exclamatory mark stands for logical notting or negation. So A greater than B condition will return B true, and not of true is false, represented 0. Okay. Now let's look at other operator called shift operator. Shift operators are used for shifting the bits of a particular number. For example, consider the variable A which is equal to 1 0 1 0. If you apply the shift operator, the left shift operator, A left shift by 1, what happens is the 0 will, the number bitwise will shift to the left. So the most significant 1 of A will be shifted out, it will be lost. Then the next 0 will come as the MSB, the next 1 will come as the next bit, the last or the least significant bit 0 will become as the third bit, and there is a gap, and that will be added with a 0 while shifting to the left. Similarly, if we perform right shift by 2, what will happen is this number will be shifted to a right once. So here also a 0 will be filled in the most significant part. Now let's look at concatenation operator. Concatenation operator, as you know, are basically used for clubbing two numbers or two vectors together. Okay, so if you write A is equal to 2 dash B 0 0 and B is equal to 2 dash B 1 0, and if I write Y is assigned with A concatenated B, what it does is it will bring to Y a 4-bit number, because these two being 2-bit, the concatenated version will be 4-bit wide of the same type binary, and first come A, what is 0 0, then comes B, which is 1 0. Now Y is a 4-bit number, which is the result of concatenation of A and B. Similarly, you look at the next example. This is an example of replication plus concatenation. Here the number A is replicated twice. So A was a 2-bit number. When you replicate it twice, you get a 4-bit number, A returned twice, 0 0 0 0. Similarly, B is replicated thrice. So it's a 6-bit number, 1 0 1 0 1 0. Now you are concatenating both using the concatenation braces. So you get A 2 times, 0 0 0 0, then B 3 times, 1 0 1 0 1 0, and that's a resulting number. And the number will be how many bits? 4 plus 6, 10-bit wide. Okay, so below is also yet another example of concatenation operator. Now let us look at another data structure in Verilog. Like most of the other languages, Verilog also has vectors and arrays. The vector represents multiple bit variable. It represents a bus, in fact. Here, whenever you find a vector specified, the left side width specifies the most significant bit of that vector. This is very, very important in understanding. We will see it with some examples. So vector assignment by position is there. So you can see the examples in the left side box. Here you can see the first declaration stands for a vector by name bus array of type wire. And what is the width of that vector? It is 3 down 0. That means it's a 4-bit vector. And what will be the most significant bit? Most significant bit would be bus A of 3, because the number close to a left side bracket will be always the most significant bit. Okay. Similarly, you look at the next, the most significant bit of the vector B, bus B would be 1. Now, you can always use this information for selecting a part of the vector. After declaring a vector and storing it with a number, if you want to select certain part, for example, in the first case, bus A is a 4-bit vector. So if you write bus A 2 down 1, it will select the bit position 2 and 1 and move to another vector bus C. So that is what is happening in the vector part select. Now let us look at what is an array. Array is slightly different. Array is a collection of the same data type. Okay, array is a collection of multiple numbers having the same data type. For example, you look here, data arrays are declared as integer, register and so on. The first declaration, my int, is an array, okay, having actually 5 rows. Okay, so if you look at the array declaration and the vector declaration, looking at itself you can distinguish between these two things. In the case, if you find the width specified after the variable name, by all chances it is a array. If you find the width specified before the variable name, it is a vector. If you find the width specified before and after the variable name, then it's an array. That is, in a nutshell, if you find the width specified after the variable name, it's an array, whether there is a width before it or not. Okay, you look at the third example. You find a width specified after the variable name mymem, so it is an array, you can fix it in that, and the first width after the variable name represents the number of rows. So this mymem is a array having 10 rows. The first row would be row 0 and the last row would be row 9. And why this width is specified? It means that each row in the memory or the array is having 8-bit wide or 8-bit width. Okay, fine. So let's just ensure that we have understood the differences with the help of certain examples, and we'll come to this. You see this declaration, you don't find a width specified after the variable name, so it is not an array, it should be a vector. Okay, and what it is meaning, it is a vector by name A register of type reg, and it is having how many, what is the size of it? It is, the size is 8-bit, and what is the most significant bit? The number close to a left side bracket is the most significant bit, that is number 7. Okay, now let's look at the next example. It's written AMM 7 down 0, so it is, the width is specified after the variable name, so it is an array. And what is the type? It is reg. What is the name? It is AMM, and the first width specifies the number of rows, so it is an array having how many rows? It's an array having 8 rows. What's the name of the first number close to a left side bracket? That is 7. So 7, 6, 5, 4, 3, 2, 1, 0 are the different rows. If you see how they are represented, in the case of vector, the first example, you find only dotted lines. That means it is actually representing one number having 8-bit width. Whereas in the next drawing, you find solid lines. That means it is an array having a collection of 8 different elements, not one number. That's the difference between a vector and an array. Let's look at a few more examples. Now you see the declaration reg bmem 7 down 0, 0 up 3. So you find the width specified after the variable name. So as we discussed, it's an array. You find 2 width specified. The first width always represents the number of rows, and the second width represents the number of columns. Okay, so here it has 8 rows, and the first row is row number 7 and the last row is row number 0, and also it has 4 columns. The first column would be column number 0 and the last column would be column number 3. Okay, so it's a 2-dimensional array of type reg. Now let us one more declaration. Here also you find the variable, the width specified after the variable name, so it is an array having how many rows? It is having 4 rows. The first row is row number 0 and the last row is row number 3, and also you find a width specified before the variable name, so that means each row is a vector having 8-bit wide, something like this. You can find 4 columns, 4 rows. The first row is row number 0, which is the most significant bit or the number close to left side bracket, and each row you can find some dotted lines having 8-bit positions. So each row can accommodate one vector. So it's an array of vector. Okay, it's not a two-dimensional array. Let's see how memories can be modeled with its concept. Memories can be modeled as an array of registers or array of vectors, you can say. Each element in the array represents a word. Okay, a word can be one bit or multiple bit. Okay, for example, let's see some examples. In the first declaration, it is written reg mem 1 bit 0 up 1023. So it means you find the bit specified after the variable name. So here it means the memory is nothing but an array having how many rows? It's an array having 1024 rows, and the first row is the number close to left side bracket, which is row position 0, and the last row is row number 1023. So total altogether 1024 rows are there. And how many bit each row can accommodate? Because you don't find any bit specified before the variable name, each row can accommodate only one bit of information. So in a nutshell, it can accommodate 1024 bits, different bits. So it is equivalent to 1 kilobit of memory. Let's look at the next example. Next example, it's declaration of another memory of type of by name membyte, and it is an array having 1024 rows. The first row is row number 0, and each row each of these 1024 rows can accommodate 1 byte information, or one 8-bit vector it can accommodate. So this declaration represent 1 kilobyte memory. Okay, so having declared it, if you want to select a particular vector or a word from a particular memory, what you should write it? You should write, say, y is equal to membyte, say 511 you have written, means the vector which is residing in the 511th row of this particular memory, membyte, okay, will be fetched and stored elsewhere where this it is assigned to. Now, two-dimensional array with now you look at this declaration. Can you just take a minute and to see whether you are able to identify what kind of memory structure it would be? Yes, of course. Since the width is specified after the variable name, it's an array. You find two widths specified, so it's a two-dimensional array. The first width represents the row, second width represents the column. So it is an array which is two-dimensional, having 4 rows and 5 columns. The first row is row number 0, and the first column is column number 0. And each row column interjunction is a cell which can accommodate 3-bit word, something like this. You can see it has 4 rows and 5 columns. At each row column interjunction you can find a cell. So that cell can accommodate a word which is having 3-bit wide, or it can accommodate a 3-bit vector in each cell. Okay, so having touched upon the arrays and vectors, let us now see another construct in Verilog, which is called a parameter. A parameter is a keyword in Verilog, so it is always written in small letter. Okay, and what is the usage of parameter? A parameter is basically used for assigning a constant to a text. Okay, so here you see certain example. It's written parameter port ID is equal to 5. So whenever in your program the compiler see the word port underscore ID, it will be read as equal to 5. So it is just like assigning a constant for repeated usage in a code. Okay, so what is the specific advantage of it? It gives you high level of scalability. So instead of writing 5 throughout in your program, you write port ID. So now you made a design which can accommodate a 5-bit data. Later you want to scale it up to say 8-bit, you simply have to change it at only one place. Parameter port ID, if you write it equal to 8, then everywhere wherever the compiler see the word port ID, it will be read as equal to 8 instead of 5. So that is the advantage of parameter. In a nutshell, it is used to assign a constant to a text. Now let's see the structure of a Verilog description by taking a simple piece of hardware which we can imagine. Let's take a 2-input AND gate with input A and B and output out. Okay. So here the terminal ports are small a, small b and small out. So as we described already, first and foremost what we should write is the keyword module. So all keywords I have shown it in a different color. So as I told, Verilog is case sensitive, all keywords must be in small letter. So after you write the keyword module, you write the module name. Module name can be in small letters or capital letters. Only constrain it should not start with a number or a special character, or it should not be a standard keyword. So I have written here AND 2. So make sure that you don't leave any space between and 2, because A and D as such is a keyword. So you can write it AND 2 or whatever name, it could be even your name. Then put a bracket and list out all the terminal ports in any order of your choice. It can be input port first or then output port, or it can be output port first then input port. It's up to you. Okay. So the bracket lists only the terminal ports. Next what we do is we declare the ports. Here A and B are input ports, so use the keyword input. Again it should be written in small letter. Similarly the keyword out is an output port. The port out is a output port, so the keyword to be used is output. Now we have declared the port. The next thing what we should do is we should write the functionality of this hardware. So this piece of hardware is a simple AND gate, so it should only do A ANDed with B. So here you find another keyword called assign, which is a keyword used in Verilog for continuous assignment. So whenever you use the keyword assign, the value of the expression on the right hand side will be computed, and at every instant of time that value will be fed to the variable on the right hand side. So out will consistently and constantly get the value of A and with B. Whenever the input changes, you can observe the change here. The out is continuously driven without waiting for the change in the output, but you can see the change in the output whenever the value of the input changes. Now once you have finished declaring the functionality, you are supposed to write the termination of the program by using the keyword end module. You notice there is a semicolon that marks the end of every line in Verilog, but there is no semicolon in the last line, and there is no space between end and module. Okay, so what you have learned here is the usage of assign. Assign is used to continuously drive the right hand side variable, the left hand side variable with the value of the expression on the right hand side. Now in Verilog there are different levels of abstractions possible, or different design styles. The design can be represented as an algorithm. That kind of representation is called behavioral model. Design can be represented in the way how data flows between different registers. That is called data flow modeling. Design can also be represented in the form of the gate level structure. That is called gate level modeling. Design, if it is simple enough, can be represented in the form of transistors. For example, it's a simple NOT gate. The structure of an inverter is given there. So in that case, you can always instantiate a PMOS and an NMOS and make the connection as per the diagram. Such descriptions are called switch level modeling. So Verilog support all these 4 levels of abstraction or 4 design styles, namely behavioral or algorithmic, data flow, gate level or structural, and the 4th one is switch level or transistor level. Okay, we will see examples written in each of these styles in the next session. The next important construct in Verilog are called system task. System tasks are nothing but some standard constructs provided by Verilog for performing certain routine operations like. So routine operations normally include initializing a variable, displaying on the screen, monitoring of variables, stopping the simulations for debugging, finishing or terminating the simulation, and so on. So what is common to all system tasks? It will have a common way of representation or a syntax. It is $ followed by a keyword. Okay, well, let's see some examples. Let's see the system task for monitoring and printing purposes. For monitoring and printing, for printing specifically, we have a system task called $display. This is how $display is used. You can find here the usage. It is written $display, and inside bracket some data is given in the quotation followed by a variable name. Okay, so here you can see there is a variable called data which is assigned as 4-bit binary value 1100, and if I written $display and made this program to run, it will print me in the console the value of data, which is data is equal to 12. Okay, because we have not specified here any output data formatting, so the default way it represents as decimal. Okay, on the other hand, if I return $display B, it will represent me the data in the binary format as 1100. Similarly, had I given $display H, it will print my data in hexadecimal and C will be produced. So $display is for displaying values of variables or strings for expression. Similarly, there is something called $monitor. $monitor is for continuously monitor changes in the values of the variables in the list. Okay, for example, see the usage below. It's written $monitor, then inside the bracket it's written %t, $time, in is equal to %b, enable is equal to %b, out is equal to %b, then after comma it is written in enable out. So here what happens is $t is an indication that you expect a time value, and the next system task called $time will print you the simulation time. Similarly, in equal to will be printed, and the binary value returned by the variable in will be printed. Okay, and so on. So just a minute. So if you are given %b, it will print the value of the variable in binary format. If you give %o, it will print the value of the variable in octa format. If you give %h, it will print the value of the variable in hexadecimal format. If nothing is given, it will print. If you give %d, it will print it in decimal format, and if you give %t, it will print the time unit. So simulation time unit is often written by another system task called $time. So if you look at what is the difference between $display and $monitor, $display is like printf in C. Okay, whenever you want to print a value, you give it inside a bracket of $display. On the other hand, $monitor is for continuous monitoring. It needs to be invoked once, whereas every time you want to print something, you have to invoke $display. $monitor, once invoked, till end of the simulation, it will continuously monitor the values of the variable in its list, and whenever the value of any variable changes, the value of all will be printed. Okay, when any one of in, enable or out changes the value, $monitor will print their current value. Okay, you can just look at this example and reinforce what we have discussed so far. The left example is for $monitor. Here you can see inside this initial box, the variable in is first given 0, then after 10 simulation, this is how you specify delay in Verilog, hash followed by a value. So after this 10 nanosecond, the value of input is made 1, then after another 10 nanosecond, the value of input is made 0. So if you have put $monitor to monitor the change in the values of output, input, then whenever the value of any of these changes, all values will be printed. For example, at 0 simulation time, what is the value of out? You can see here it is driving a NOT gate. So whatever is in the input, the opposite should be there in the output. So its simulation time unit 0. Okay, you should get the output of it. Okay. at one simulation time unit. At 0 simulation time unit, basically what you're getting is the input is made 0. Okay, so obviously you expect the output to be 1. But if you look here, when you declare the NOT gate, there is another delay of 1 nanosecond specified. So whatever you give it to the input of this NOT gate, it takes another 1 nanosecond propagation delay kind of thing to reach the output. So at 0 simulation time unit, there is no change in the output. So output will get the default value. Okay, and output will be driven with the default value, and in the input, when the input changes to 0, after 1 nanosecond, the output will become the opposite value of it. Similarly, at the end of another 10 nanosecond, the value will become 1 only, because at 10 nanosecond you are making input 1. Then at 11 nanosecond, after this delay, it will become 0 and so on. But in the case of monitor, you can, in the case of display, which is shown in the right hand side, you have written display under the initial, and you can find only the last value will be taken into consideration. Okay, so that's difference between monitor and display. As I explained earlier, monitor need to be invoked only once. It will continuously monitor changes in the values of the variables in its list, whereas display, every time you want to display something, you have to give separate display. Now let's see the system task for stopping and finishing the simulation. $sign stop is a system task which stops the current simulation and puts the compiler in the debug mode. Okay. Similarly, $sign finish, it is also used for stopping the simulation, not only stopping the simulation but also basically terminating the simulation and to quit the compiler. So here you look at this example. Initially clock is made 0 and reset is made 1. Then at 200 nanosecond or 200 simulation time unit, because of $sign stop, the simulation will stop and the compiler will be put in interactive mode where you can debug your code. At 200 plus 800, 1000 simulation time units, the program will be terminated and it will be asked if we can close the compiler. It will be prompted for closing or quitting the compiler. Now there is another special type of constructs in Verilog called compiler directive. Compiler directives are basically instructions to compiler to perform certain specific task. So often compiler directives comes with a syntax tick followed by a keyword. For example, tick define is a keyword which is used for substitution. So whenever you write, say, tick followed by a text name followed by a value, whenever the compiler sees that text name, that will be read as equal to that value. For example, you see the usage below, it is written tick define halt 3-HO, tick define skz 3-H1. So whenever we further use HLT with a tick mark, the compiler will be reading it as equal to 3-H0. Whenever it see the opcode tick skz, it will be read as equal to 1. Okay, so just like what we have parameter here, this is yet another method for assigning a string or a constant value to a text macro. The next compiler directive is used for time scaling. It is called tick time scale, and the usage is like this: tick time scale followed by time unit / time precision. For example, you see the code which is written on the bottom. It is written tick time scale 10 nanoseconds / 1 picosecond. So wherever now your compiler see a delay specified, it will be taken as the multiple of this particular delay. So 1 means 1 into 10 nanosecond delay. 2 means 2 into 10 20 nanosecond delay. 1 means again 10 nanosecond. And what about the next 1 picosecond? It means it has a precision, or it has a tolerance of 1 picosecond. Okay, so something which is happen at 10 nanosecond may happen at 9 nanosecond or 11 nanosecond. So that much tolerance you are adding by adding this time precision value. Now, having familiarized with most of the language or lexical conventions or constructs, let us revisit our initial problem of designing a magnitude comparator with input A and B 3 bit each wide, and the output A equal to B, A less than B or greater than B. We have seen it in the schematic point of view. It's quite difficult to come up with an sum of product expression and thereby to draw a combinational circuit for this, because it is having minimum of 2 to the power of 6 combination. In the actual hardware it is not even 2 to the power of 6 combination, because in a hardware there are 4 possible data values, 0, 1, x and z. So actually it can have 4 to the power of 6 combination, which is quite difficult task to reduce itself to a sum of product expression. But with the Verilog, you can see that it's quite simple. So if you want to describe this hardware, as normal we write the keyword module, then some module name, then list of all terminal ports, which are nothing but capital A, capital B, A less than B, A greater than B, A equal to B. So that completes my port listing. Next I have to declare my ports. So I'm writing A and B as input port, which are actually 3 bit wide. So I can write 2 down 0 or 0 up 2, or I can write 3 down 1 and so on. So basically I have declared A and B as vectors of type input. Then I am declaring the output ports are all 1 bit or scalar ports, A less than B, A greater than B, or A equal to B. Now it's time for me to write the functionality. So basically this is a magnitude comparator. Given whatever value to A and B, either A is equal to B, or A is greater than B, or A is less than B. Okay, so one of these output only should be high at a time. It's similar to one hot encoding. So I can write these lines. Assign A less than B is equal to A less than B. So this expression will return me 1 if and only if A is actually less than B. Else it will return me 0. Similarly, A is equal to B is assigned with A double equal to B. That is this equality checking. A greater than B checks if A is greater than B. So whatever value you assign for A and B at any given point of time, only one of these output will be high, the others being mutually exclusive. We have finished writing the functionality of this hardware and we are good to write the end module. So if you look at it, the functionality here is represented in just 3 lines. Now compare how easier this HDL way of design entry will be compared to an equivalent schematic entry. Ultimately, whether you enter it as a schematic or you enter it as an HDL, the synthesis tool is converting into a structural equivalent. Okay, so from a designer perspective, design entry using HDL is a breeze compared to the same using its schematic counterpart. So that's a point which I wanted to impress, to clearly tell you the motivation for learning hardware description language. So thank you. So in this session we have seen the background of why we should go for a hardware description language and the way it is used in the VLSI design flow, what are its advantages. We have seen certain resources which you can depend upon in further learning Verilog. We have also seen certain lexical conventions like types of ports in Verilog. We have seen the data type. The ports can be classified based upon width as scalar and vector. Ports can be classified based upon data type into 2 fundamental types, net data type and register data type. The important keyword in registered data type are REG, real, integer and time. REG is used for storing unsigned numbers, integer is used for storing signed numbers, real is used for representing floating point number with double precision, time is used for storing simulation time units. We have also seen net data type. The most important keyword is wire. The default value of wire is high impedance. The default value of register is X. We have also seen the classification of ports based upon where it can terminate. It can be input port, output port as well as in-out port to represent the bidirectional ports. We have seen 9 classes of operators in Verilog, like arithmetic operator, logical operators, relational operator, conditional operator, concatenation operator. Then we have also seen replication operators, reduction operators and so on. We have also seen how numbers are represented in Verilog. The syntax is size of the number, a tick mark, base or radix of the number followed by the actual number. We have seen certain nitty-gritties of how numbers will get truncated or zero filled depending upon the size specification. If no size is specified, the compiler will automatically assign it a size. Typically it is 32-bit. If no base is specified, the default base is decimal. We have also seen how arrays and vectors differ and what are these data structures. Arrays represent a collection of n different numbers, whereas a vector represent a number which is a multiple bit wide. We have also seen compiler directives for substituting a text, for including a text, and so on. We also seen system tasks like $stop, $finish. $stop will stop the simulation and put the compiler in interactive debug mode. $finish will terminate the program and quit the compiler. Similarly, $monitor is like printf in C. Every time you want to print something, you can give a $display followed by the list of variables you need to print the values of. $monitor is another way of monitoring the values of the variables in its sensitivity list. It need to be invoked only once. Once it is invoked, it will continuously monitor changes of the values of all variables in its list. So this is what we discussed in this session. Thank you.